What are the chances of getting earache from swimming in the sea? Out of the Blue now has the answer.
Shoebury-Ness is one of 5 beaches at Southend-on-Sea and has consistently met the European standards for the quality of its bathing water. At the height of the summer, this part of the Thames estuary becomes a very popular tourist resort. Keeping the concerns of the bathers in mind, Southend-on-Sea pursue a policy of monitoring the quality of bathing water. In fact, they were the first council in the UK to display the results on resort reports. These reports give the results for all 5 beaches on a pass or fail basis at a number of locations right along the seafront. As part of the efforts to improve the pass rates, a deep water sewage outfall was extended in the late 80s beyond the low water mark, right out into the deep water channels used by shipping. Strong currents then carry the sewage out to sea, where the bacteria are dispersed and die. Further improvements are being made to the outfall system all the time, and so failures in bathing water quality will eventually be eliminated. So the National Rivers Authority and the local water company are investing huge resources to comply with European standards. But once the tests are passed, does that automatically mean that it's totally safe to come into contact with the water? As late as 1992-93, the prevailing European directives for acceptable bathing water quality were openly disputed. Some agencies questioned the data upon which the directives were based. Is the fact that sewage is being pumped out to sea, even a mile or so away, nevertheless still a risk to health? Or is it just an unpleasant thought? Statistical modelling can answer questions like this, and we'll be coming back to a study around our shores later. But let's look back to a couple of examples which have been modelled successfully. To begin with, a few years ago, the Australians studied the health risks of swimming in, of all places, the beautiful Bondi Beach.
Hi, this is Liz Johnson from the Waterboard Surf Line. Conditions this morning at the beach look great, with a light offshore breeze blowing at the moment.
You see, at one time sewage pollution around the beach got so bad that an ominous brown slick was easily visible, just offshore. In 1988, protesters took to the streets of Sydney to try and persuade the local water board to do something about that massive slick.
2,000 members of the People Opposing Ocean Outfalls group joined a colourful march to Bondi Beach this afternoon, calling for action to stop the pollution on Sydney's beaches.
The water board responded with plans to extend the sewage outfall to some 3 miles away from the shore. They also undertook a pilot survey to study the question of whether or not there was a statistically detectable health hazard from sewage effluent.
I got the report this morning for Bondi.
At Macquarie University, we were given the task of analysing the data on ear infections suffered by 278 swimmers in a season. Ear infections were identified as a suitable measure because they were known to be waterborne, and unlike other infections such as gastroenteritis, not likely to be affected by what people were eating. Some of the data they collected can be represented by plotting the number of swimmers against the number of ear infections they had. No infections at all were reported by 151 swimmers in the season. A single ear infection was experienced by 40 swimmers. 2 ear infections were reported by 39 swimmers. 3 infections for 26 swimmers, 4 infections for 13, 5 for 5, and 6 ear infections for 4 swimmers. So the pattern is one where over half were infection-free and the rest got between 1 and 6 ear infections in a season. What's required is to find a way of explaining the whole underlying pattern, and that means using a probability model. If we can explain the pattern, hopefully we can not only assess the risks to swimmers, but also, and more important, get some idea of what it is that puts them at risk. We're entitled to make 3 assumptions. Imagine you are a swimmer. On any one day, you'll have the same chance of picking up an infection as on any other day. Getting an infection on one occasion doesn't depend on whether or not you've had an infection before. The chances of contracting 2 infections simultaneously are negligible. As a statistician, I know that with these assumptions, I can employ at least 2 probability models.
Over the years, probability modelling based on assumptions like these has been applied to a wide variety of areas. You might not recognise this beast. It comes from the Second World War. It's a German V1 bomb, a doodlebug, here on its launch ramp on show at the Imperial War Museum site at Duxford. I'm going to show you an interesting bit of history concerning the effect of these V1s, because that's going to lead to a useful way of thinking about modelling ear infections. Altogether, nearly 10,000 of these flying bombs were launched against British towns in the autumn of 1944. Considerable resources were devoted to attempts to bring them down, but large numbers got through nevertheless. The majority descended on London. The German V1 campaign caused justifiable panic amongst the general public. The dangerous time was when the engine cut out. Each bomb was capable of flattening a building and causing further death and injury over a wide area surrounding the impact. Behind the scenes here at the Imperial War Museum at Duxford are many of the artefacts of that period. This is a map, which is the original map made by the London Fire Brigade. It shows the V1 hits, they're the brown pins, and later the V2s, the blue pins. You can see the scattering of bomb hits, but is it a recognisable pattern? For example, this cluster of hits here, is it significant? It's very difficult to tell, but it is important to answer the question, could the V1 bomb be aimed precisely or not? At the time, the general public, as well as the military authorities, wanted to know, is the V1 an accurate weapon, or is it nothing more than a crude anti-personnel weapon? Well, if the bomb's designers were to be believed, it was a very capable device.
Das Ziel ist erreicht. Abstieg, Einschlag. Das Gerät wird zur Bekämpfung von Flächenzielen eingesetzt. In der Mitte das Trefferquadrat. Die Einschläge geben ein Bild von der Treffgenauigkeit, die den Forderungen des Einsatzes entspricht.
In other words, the Germans claimed a fair bit of accuracy. But was it just exaggerated propaganda? You can't really tell directly from this without doing some statistical analysis. And you can show that in fact they were not aimed. First, you have to extract a statistical pattern from these data points. In 1944 they did this by taking a 36 square kilometre area of South London, and they gridded that into quarter-kilometre squares. You end up with 576 quarter-kilometre squares. The number of bombs which fell totalled 537, giving a rate of 537 divided by 576 hits per square, which is in fact 0.932 hits per square. But as you might expect, there was quite a variation. Some squares were bomb-free, whereas the inhabitants of one square received a total of 7. You can represent these data in the same way as for the swimmers. Count the number of squares with no hits, the number with one hit, and so on. With a vertical axis again for frequency, and a horizontal measure for hits within a square, you can build up a pattern. 229 squares were missed. 211 have a single hit. 93 suffered 2 hits. 35, 3 hits. 7 had 4. And that one fated square that had 7 hits. Of course, that result barely registers on this scale. So you can extract a pattern, but how do you set about interpreting it and explaining it? How about starting with the assumption that the bombs couldn't be accurately aimed, but were randomly distributed? Let's concentrate on a single quarter-kilometre square. Up here, in central London, is an area which would surely have been an important target: London Docks. Here are some RAF reconnaissance photographs of Docklands, taken just before the end of the war. Let's get some idea of scale by gridding it with quarter-kilometre squares. And let's look at one square in more detail. This is Millwall Dock. You can make out a vessel of some sort, warehouses, even railway carriages, if you look closely enough. Now, if a bomb fell in the square, you get a crater about this size. Call it a crater square. There are about 900 such squares in the quarter-kilometre square area. Now remember, the rate of hits per quarter-kilometre square was 0.932. So the rate of hits in a crater square is 0.932 over 900. And it's going to be the same for each one of the crater squares, because, firstly, a hit at one crater square is no more or less likely than a hit in another, say here. In each case, the rate of hits is the same, 0.932 over 900. Secondly, the fact that a bomb landed here has no influence over whether or not another one lands over there, say. And thirdly, no bomb is appreciably likely to fall down the same hole as another. So the assumptions are: a hit at one point is no more likely than a hit at some other point. Where one bomb lands isn't influenced in any way by where another has landed. There is a negligible chance of a bomb dropping directly into a previous crater. So you can say that you've got 900 squares, each of which may be independently hit by, at most, one bomb. What you've set up is a classic distribution based on a number of independent Bernoulli trials. In other words, you have a binomial distribution. It's the distribution for the number of successes in a number of independent trials. You have n squares, or trials, each with probability 0.932 divided by n of a hit. For the total of 900 crater-sized squares, this is the predicted distribution. How does the binomial distribution for one quarter-kilometre square compare with the data for the whole 36 square kilometre region of South London? Well, the proportions will stay the same, but scaling up over 576 squares, you get this. And these were the actual numbers that the fire brigade reported. And there's a remarkable fit. Now that indicates the assumptions were good ones, and the bombs were indeed falling randomly. They couldn't aim them at all well. Now that distribution depends upon 3 assumptions about randomness. And if you think back to the assumptions made about ear infections, you'll see they're very similar. The first assumption, that a bomb has the same chance anywhere, is equivalent to saying the same infection chance whenever you swim. Secondly, in both cases, they're independent events. And thirdly, no more than one bomb in a crater square corresponds to no more than one infection at a time. At first sight, these assumptions seem to correspond perfectly, but there's a slight problem with the last one. A crater square forms a logical basic unit of area. There's no similar guide for a logical basic unit of infection time. But how important is the idea of subdivision into crater-sized bits? For the single square, subdividing into 900 squares seemed reasonable and gave this modelling distribution. Does it make a big difference only dividing into, say, 400 squares? That's 20 by 20 smaller squares. The bar chart for 400 squares looks much the same as the last one. They're almost indistinguishable. In fact, they are indistinguishable. Perhaps then, for a binomial of this form, the n doesn't matter very much, if it's large enough. It can be shown that if you let n tend to infinity for this kind of binomial distribution, you get another distribution which depends only on the rate. In this case, the 0.932. It's called a Poisson distribution. And for 0.932, it has this same shape. For large enough n, a binomial n, 0.932 over n, is so close to it that you can't see the difference. You can check on that by comparing them, starting with a low value, n equals 5. Then draw in the bars for the binomial, 5, 0.932 over 5. Quite a bit different, especially on the left. But suppose n is increased to 10. And 30. It's getting closer. And 60. Hardly any difference now. Certainly for 100, 400, 900, you can't tell them apart. So the beauty of using a Poisson distribution is that you don't need to think about crater-sized squares. All you need to think about is the rate. That is, the number of events per unit area. In this case, the number of hits per quarter kilometre square. And for the swimmers, it's number of ear infections per person in a season. For a binomial model, you would have to subdivide person seasons. But for the Poisson model, you just need the rate. That's the average number of ear infections per person in a season. And surely that's just the sort of model that Don McNeill and his team can use.
Considering the assumptions we've made in order to analyse the swimming data, it seems obvious to try to utilise the Poisson distribution. That means all we need is the average rate of infection over the whole season. There were 278 swimmers and a total of 297 reported infections among them, so the rate is 1.068 infections per swimmer throughout the season. The Poisson distribution with this rate looks like this. But the observed results look like this. You can't call that a fit. The fact that the model doesn't fit is telling us something. What could it be? The assumptions are plausible, but there's an extra little one which isn't obvious. Many swimmers do most of their swimming in the sea, but many swim in a pool with chlorinated water. So there are at least two different groups to consider. And the story can get even more involved because some swimmers swim daily and others swim less often, say once a week or only once a month. It's even more involved than that. In fact, the Poisson rates may be different for males and females, for old and young swimmers, with just 4 possible alternatives: pool or beach, frequent or infrequent, male or female, and old or young. There are already 16 subgroups, each with its own Poisson rate, which could be modelled. Consider, for example, the 23 individuals who were males, aged 20 and over, and frequently swam in the sea. Between them, they suffered 16 ear infections over a season. which gives this group its own infection rate of 0.696. The Poisson model with this rate predicts that those 23 individuals will be distributed like this. Do the same exercise for each of the other 15 different groups. Stack them all up, and you get this prediction for the entire 278 swimmers. And comparing with the observed data, you can see that the prediction fits. So what do you do with that information? Well, the basic question was the effect of sewage. So assuming that swimming in a pool removes the question of sewage, let's look at pools versus beaches. Here the two sets of data have been separated into pool swimmers and sea swimmers. The models still fit the observed data, but consistently the beach groups on the left had higher average Poisson rates than the pool groups on the right. Overall, the infection rate is significantly smaller for pool swimming than sea swimming, and considering the sewage, that can surely be no coincidence.
So the Australian verdict isn't very surprising. They've identified a significant hazard associated with swimming in the neighbourhood of sewage outlets. The logical next step is to find out what it is in the water that's especially dangerous and in what concentrations. If you're rigorous enough in your survey, you can investigate not only ear infections, but also a variety of other ones. Once again, Southend has been in the vanguard. Over 400 healthy volunteers have been taking part in a study, where one group swim in the sea for a set period of time, properly supervised by marshals.
10 more minutes and you can come out.
And another group, selected at random from the volunteers, simply have a picnic on the beach. The water is sampled at regular intervals and at known locations, and then tested in a mobile lab by a team from the Centre for Research into Environment and Health.
We targeted beaches that pass the present European directive levels, and in those beaches that pass those directive levels we're looking for health effects. If we find them, it may indicate the current standards require tightening. If we don't find them, they may be quite adequate. But clearly we're doing much more intensive water quality sampling here than one would normally do for compliance assessment.
Do you have any long-standing...
Before they go on the beach, the volunteers are screened by way of a general health questionnaire. They then undergo a thorough medical examination. Many infections have quite a long incubation period, so both bathers and non-swimmers are examined after a week, and then again after 3 weeks with a follow-up questionnaire.
In our first study, which is now being published, we found excess rates in the bather and the non-bather group of the order of 10 to 40 per thousand of minor symptoms, things like upper respiratory tract symptoms, things like gastroenteritis. Those are the sorts of rates, which is largely in accordance with other studies. What other studies haven't really done is sample the water in sufficient detail to try and tie those rates to particular water qualities.
Earlier on then, you saw examples of two widely differing data sets, buzz bombs and ear infections in swimmers. And the modelling assumptions turned out to be the same. Hopefully, the data from Southend will lead to a clearly defined bathing water standard. They'll require a more sophisticated analysis, but even so, the basic technique of building a model from common sense assumptions will still apply.
There's a change of program.